Hi, welcome to ProDrive's Emotions Secret Labs located in Taipei, Taiwan. I think today we're very excited because we want to introduce something that we will be showing in the coming Tokyo Techno Frontier 2015 exhibition. It's about motion technologies. What we're about to demonstrate here is a brick and mortar device. It's a hybrid composite speed reducer. It is made up of 3 layers of different types of speed reducers. The first layer is a planetary, traditional, conventional planetary gear reducer. It has a gear ratios of 1 to 5.45. And the second layer is what we call the PDS-TD. It's a planetary device with a small number of teeth difference, which give us a layer of speed reduction at 33.67. The third layer is a very unique cam wave speed reducer. It's our special cam drive that we innovate here. It's a patent drive. Because of this third layer makes this hybrid drive very powerful and unique. And we're getting very excited to introduce this to the world. So it provides a gear ratios about 28 that makes this total composite gear ratios at about 1 to 5,042. And what you're about to see is a device that we designed to provide. Although under such a high gear ratio, we only designed it to have a torsional load, nominal load, at about 50 Newton meter. But then during the test that we are demonstrating, you're gonna see that we're pushing it to extreme, maybe not reaching the 200 Newton meter, but maybe close to somewhat 150, 160 or so. We have a little dimensions here. If you look at this box, this is the composite drive that we were talking about. This portion here is the composite gear reducer. And this portion right here is a brushless motor, which we have our own controller that controls the motions, control the angle, the speed, and so on. If you look at the dimensions, the size, the cross-sectional size right here, it's about 59.4 millimeter square. And the total length here, this part is the 26.5, and this part is the 64.7, which made a total of 91.2 millimeter. The demonstration is going to be given in such a way that we want to show you what's so excited about. First of all, this composite drive, because of the third layer of the OCam, which is our CamWave speed reducer, it provides the spindle lock, and which means it will maintain at the last power position. And it also provides no backlash, what we call the no loss motion. This will, in relation to at the control side, a very precise positioning. It's a very compact and it's very strong. We often refer it to as bricks and mortar type of speed reducers. So what's gonna happen is we're gonna you should see the weight here. This is 10 kilogram weight each. We have 20. We have 2 of them, which make a total of 20 kilo, mounted on a lever of 25 centimeter, which is 0.25 meter. This makes it approximately 50 Newton meters when it's spinning on the horizontal position, because the gravitation, it provides a full weight of 20 kilo at a 0.25 meter lever arm and makes it a total of approximately 50 Newton meter load and constantly spinning. But I'm not going to show the whole movie of what's spinning. What I'm going to show is we're going to show maybe one full circle of running at the clockwise and the counterclockwise direction. And you're going to see when it comes to the full load, the current can run between 1.2 amps to about 2.6 amps. And when you reverse the direction, the current runs about 1.5 versus 2.1, depending on the spinning direction. At the top and the bottom, where we refer to as no load conditions, it's running about 0.7 amps. So I'm going to run 2 complete runs and let you see that the current, the drawn from the power supply here, which we set at 18 volts. We set a current limit at about 10 amps. And when it started functioning, the device, the motor here, is going to draw up to about 2.6 amps during the revolutions. And this is under the normal, what we call the nominal load at a 50 Newton meter situation. So that's the normal operation. I guess it's not really exciting, because nothing to be excited about, because you can see that almost anywhere, anytime. What's going to happen is during this, right after this normal operation, I'm going to ask my colleague to come in to help me push this thing to the extreme. And push to extreme could be either put it under 200 Newton meter load, or I try to abuse the device, push it, knock it, maybe even write on it. And then we're going to see, before we abuse it, what the current situation is, and after we abuse it, and we're going to see afterwards, can the device still running? Can the device still be running properly, normally? And then we can get excited, because this often indicates a device that during its operation, when power gets interrupted, is the device very safe, will remain at its last power position, or is it accurate enough? We can use this accuracy to automate some motions very accurately. So this is an introduction about what we're about to demonstrate. And now I'm going to be running some normal operation to demonstrate what I just mentioned about the current. So here I'm going to be turning on this control box and let it start spinning. Now you can hear the noise is a little bit noisy, is because we have some vibration, resonance taking place here. This is a hollow lab. Okay, it's reaching a position where you can see the currents coming up at about 1.2, 1.3, 1.3 max. So, in this direction. And it's going into the lowest position and reaching about should be in the 0.7 range, where you can see that 0.6 something. So that's what we expect. Now it's coming back up. You probably see some current fluctuating. That's because this device has been going through 5,000 cycle live tests already. A little bit worn out, but still running like a charm. Okay, it's coming back up at about 2.5, 2.6, 2.6 when it's passing through the horizontal 50 Newton meter load condition. So now it's coming back up at the starting position, and it's reaching at about 0.6, 0.7, like I said. Okay, now I'm gonna reverse the direction. So now it's spinning at the other direction, where we can still see the current coming back down to 0.6 at the high position, or the zero no load position, and it's coming down to the horizontal, where on the board you can see that we predict this is to be about 1.5 amps. So it just passed through 1.4 something, 1.5 a flash. Going back down, we should be seeing about 0.6, 0.7 amps at the lowest point, no load. Then coming back up to the other way of the 50 Newton meter, which we expect to see about 2.1 amps or 2.2, depends on it. So coming back up, almost there. 2.0, 2.0. Alright, so 2 amps. I don't see any flashes above 2.1. So it's about to come to a stop. And I'm gonna stop it here. Please take a note on this. I'm gonna turn this off by the control box. So you can see that as soon as I turn it off, it's still running. That's because of the delay settings on the control box. It's so that it doesn't cut the power off, but just drop the PWM off the motor and come to a complete stop. Maybe a tenth or 2/10 or 3/10 of a second. But when I mentioned about the last power position, later on I can show that when actually I can show that right now. So I'm gonna turn this on again, and I'm gonna turn this power off right here. I'm gonna turn this off. 1, 2, 3, off. See, there's no kind of like extended motion. As soon as I turn the power off, it's actually stopped right there. No movement. I'm gonna get help from my colleague. I'm gonna put a pause to this video filming. I'm gonna ask my colleagues to come and do some test on this thing, either in motion or no motion, just to show that how strong, how robust, the rigidity, the running of this thing is. Remember, this is a design of a 50 Newton meter load on this about 18.5 millimeter shaft. We could have the shaft load at about 250 Newton meter, but the other accompanying mechanical structure, we didn't make it too strong because this is only a lab version. We actually have a product in production for 1,000 Newton meter load for a customer doing the sound tracking device. So it was really exciting. The nominal load of that device is about 680 Newton meter, and but we put it to the maximum load at about 1,000 Newton meter. Anyway, so let me put a pause and bring my colleague here to do some amusement or abusement. Hang on. Okay, so I here have my colleague Kevin. I'm asking Kevin's help to try to do something to abuse, to try to push this thing to the extreme. Kevin, can you move that? Can you try to move that? Can you move it? Okay, not yet. Seems like can't really move it. Okay, all right. Can you hammer it? Do you want to try hammer it? Use the hammer maybe?
Are you sure?
Yeah, I'm very sure, Kevin. Go ahead and try it. Yeah, go ahead. All right. All right, don't break it, please. Okay. All right, okay. All right. I think you just broke it. All right. All right, so what else can you do, Kevin? What else can you do? You want to try something to the extreme? How about playing monkey?
Are you sure?
I think you did that already. You want to try it again? Whoa, what are you doing? Your feet are off the ground. Okay. I think you've done enough damage. All right, thank you, Kevin. All right, so my colleague had done so many things. All right, I want to try this one more time. Let me try what I did before. All right. I hope it's still running properly. Looks like current's still okay. No big deal. About 0.6 as it should. And coming back up. Now we're coming back to, should be about 2.1. Alright, so we're at about 2 amps. I don't see any 2.1 yet. Alright, and then we should be coming to about 0.6. 0.7, all right, 0.6, 0.7, and going the other way to about 1.5, not even 1.5. And now we're going down. That should be enough. Let me reverse it. Check the other direction. Alright, so coming back up, we should be seeing about 2.6. No, I don't see any 2.6. 2.4. Then coming back up to about 0.6, I hope. Point 6, 0.5, okay. Sounds good. We should be reaching about 1.2 in this direction. Looks good. Looks good. And going back down to about 0.6, 0.7. right? 0.7, 0.6. Okay, so I'm excited. I don't know if you as a viewer, are you excited? Same excited as we are. But this thing is probably into the 5,000, maybe half 5,500 cycles test already, and it's still running like a charm. We're excited because this is such compact device with such a simple mechanism within such a small space constraint, and yet it's exerting such big power. I mean, I can try to, hold this. I don't think I can hold it, stop it from not moving. I can increase the current, but I cannot stop it. So we've done this in the 5,000 test course. We try to do push to extreme, and it's still running. We're very, very excited, and I hope you are. This is a small movie that we make to get people excited, and we hope to invite people to come see us in Tokyo. So, Tokyo, 2015 Techno Frontier. If you, I'm gonna put it on the film so you see it. We're gonna show this in there. And of course, you can see that we also are attaching something we call a torque sensor here. And this is a PCB in development associated with the torque sensor. At the end, the PCB would probably be about 2/3 of this panel size. And is taking the power directly from the 18 volt. We simulate 18 volt battery to power this thing up to to give motions, and through this to detect what kind of load is on the shaft. We're excited. We're very, very excited. And we hope we have visitors, we have customers come and see us. We're inviting you to come and get excited with us, because if you are really sick and tired of the same options every time when you try to be creative, you want a new speed reducer, but you have no choice. Always one out of those three companies, and you have no other options. I think you're very, very frustrated. Well, if you are, come see us. You're gonna find something exciting and new. Why not? Just a very close trip to Tokyo, and you'll see us. I give you our booth number on our website. You can check. Most information will be put there, and check it out. We look forward to seeing you.